Hello everyone. Today I want to introduce a systematic way to solve the time-independent perturbation theory. First of all, let's look at the Hamiltonian. Hamiltonian often can be in quantum mechanics can often write in this way: h0, h1, and we often assume that h0 is much bigger than h1. In other words, the eigenvalues of the h0 should be a lot larger than h1. And also we assume that h0 is exactly solved. So we have there its eigenvalues en0, a set of eigenvalues with and their correspondent eigenvectors en0. This is the state vector. So we have the equations en0 goes to en0. But we want to solve the problems is this en. These eigenvalue problems. So we can expand them with orders. We assume en equals to en0 plus 1, and we assume that en1 en0 much bigger. 2, we have this kind of the solutions, and it can be right in the k from 0 to infinity. It's better to write like this. We just take out the en0 and plus k from 1 to infinity lambda k en(k). Often we only take to the second order, so it doesn't have to calculate to the very large order. And the eigenvectors can be expanded in this way: n0 plus to infinity lambda k en(k). So here we have another assumption that we can assume that en0 is orthogonal with has an orthogonal relation with en(k), and they are orthogonal vectors. And this is very we can always know if the en(k) does not equals to their inner product is not equals to zeros, we can always take absorb the en(k) to en0. So here is our basic assumptions. So we just take these expansions to the original equations, so we can get. So first of all, we calculate the left-hand side. Here we can see 0 Hamiltonian can be right h1. So left-hand side equals to h1 en0 plus some k from 1 to infinity lambda k en(k). And equals to h0 plus lambda h1 e0 plus k h0 e and k. the plus k from 1 to infinity lambda k plus 1 h1 e n k. And with these terms, we can absorb the two sum from 1 lambda k e n k minus 1. This term can be writing abbreviations in this way. So here we come to h0 0 plus sum from k to 1 to infinity lambda k h0 k plus h1 e and k minus 1. So this is our left hand side. Let's calculate the right hand side. Right hand side can write in this way. And then we take the part, this part, plus sigma k from 1 to infinity. So 0 plus k. So we have the n0 you can sum these regroup these categorized by lambda k, sigma p from 0 to k, p and k minus p. So we just do some compare the coefficients of each order. Compare coefficient of the lambda k order. First of all, k equals to the 0 order is trivial. It has a relation of the 0th order. This is our has already solved. So has already been solved. So there's no need to care about. Now for k larger than 1, we have the relations. Compare the left and the right hand side, the case order. For left hand side, we have h1 e and k minus 1 plus h0 e and k, and right hand side equals to this, equals to sum from p to 0, sum p from 0 to k e and p and e and k minus p. First of all, we want to calculate the eigenvalue, new correction e and k. We can just do the left action e and 0 on this formula. We have the e and 0 h1 e and k minus 1 plus n0 So we observe the first term, and this term cannot be simplified. And this term, h0, this equals to e n 0, En 0, and the inner product of the E and K. By assumption, this term equals to 0. And the right hand side, by the basic assumptions, this part only k minus p equals to 0, and this part won't be vanished. So this the p equals to k. So the right hand side is the E and K, and left hand side is n 0 h1 E and K minus 1. So we calculate the energy correction of the H order E and K equals to E and 0 and K minus 1. So our first job has done. We calculate the case order eigenvalue correction E and K. This is a very important formula. Then we need to calculate the state correction of the E and K. To find this is quite difficult, but we can expand this because this is the 0. This is the orthonormal base. We can expand them by this orthonormal base. Sum m0 and k em0. So by assumptions, m does not equal to n because the E and ek0 equals to 0 by basic assumption. So we only need to calculate the EM, the inner product EM0 E and K. And we do left action on this basic formula. So we have the EM 1 E and K minus 1 plus H0 E and K. Sum from the 0 to K EMP EM0 E and K minus P. So let's observe each term. This term cannot be simplified. As this term becomes to EM0 and K. The right hand side for P equals to 0 because EN0 equals to 0 and P equals to K. We have the basic and we have the equals to K equals to K, and therefore P equals to 0. And for 0 we have the EMP EN0 EM0 plus ENK. So we just take out these two terms out and leave the rest of the terms. and we combine these two terms. We move this to the left, so we have the m0 minus en0 nk, and we move this to the right hand side, equals to this equals to minus em0 h1 enk minus 1. And the plus sum k from 1 to k minus 1. So we have the emp 0 enk minus p. So the em0 k equals to minus emp So here we have calculated the coefficient of the each part of this formula. So to calculate the case orders, we need to calculate the k minus 1th orders and the all other lower orders problems. So we can start from the very simple examples from the first order perturbation series. In today's part, we only consider the problems of the non-degenerate case. This is also will be shown you in your quantum mechanics textbooks. But in the next part, I will introduce how to use this formula to treat the degeneration cases, which is much more complicated. So let's treat the simpler problems, the non-degenerate case. And the first order. First order perturbation. This is quite easy. First, we use the calculate the eigenvalue enk. We use this formula. Copy. E. Anyway, just copy it. Enk equals to en k minus 1 for the first order perturbation. K equals to 1, so enk equals to en1 equals to 0. 0. This is the diagonal part of the H1 H1 Hamiltonian in H0 representations. Here, I don't want to explain too much about the physical meanings because these physical meanings have been given in your quantum mechanics textbooks. I only want to give you the details of the calculation. And after we calculate the the first order eigenvalue correction, we want to calculate the correction of the vector state, which means the En1 equals to some m not equal to n em0 em0. M0. So we need to calculate this part. 0 equals to n1. The inner product, the way you use this formula. Okay, just copy it here. Just need to observe this part. The first part is m0 h1 e and k minus 1, k equals to 1, so this is 0. And em0 and k0. Now we look at the second part because k equals to 0, but p is sum from 1, so the second part vanish. So this is the first order correction. So complete en1 equals to same sum m not equals to n from 0 minus en0 in 0. So we have solved the first order perturbation problems. Now we continue to the second order perturbation. And en2 equals to en0 h1 en k minus 1 k equals 2, so here is en1, and we take the formula of the en1, so we can get zero h1 m0, and we take these coefficients. So we change these two terms with this minus sign. So we have en0 And to calculate the state corrections, and let's go to the next page, and the state correction, we only need to calculate em0 to the inner product of the em0 to n2. So the first part is em. Let's look at the formula again. First part, m0 h1 enk minus 1 k equals 2, so here is 1, and en0 minus em0, and sum p from 1 to k minus 1, this is 1, so only has the 1, so p equals to 1, e1 em0 en2 minus 1 m0 minus en0. Let's check it. This is right exactly. Here is en0 minus em0, and there is a minus sign. Okay. No, there's no minus sign because this is en minus em, not the em minus en. Here we just take the expression of the en1 to these formulas. The first part equals to sigma L n L0 and the second part becomes to en1 sum from the en1 is L not equals to n. Zero, and this becomes en0 minus el0. So this is the delta function, delta ml with some l, because m does not equals to n. So we have the formula of this formula equals to e1 over em0 minus en0 square. There is a minus sign. Okay, we have solved the first and the second order perturbation theory in the non-degenerated case. In the next part, I will continue to solve the degenerate case. Thank you.